Hello everyone. Am I audible? Yeah. So, yeah, I'm working as a research fellow at National University of Singapore, and today I'm going to present our paper toward optimal MCDC test case generation. And my co-authors are Dr. Sanratna Godbole, Professor Jackson Jaffer, and Dr. Rasul. So, our work has been accepted in the technical track as well as for in the poster track in ISTA 2021, and also we have obtained the batches as available, functional and reusable in the artifact evaluation, and these are our websites. So this is I will start with the outline of my talk. We'll see some introduction, then I will present a survey that we have performed with industrial practitioners to know more about the present MCDC tools and techniques, and then I will discuss the proposed idea. After that, I will present the results that we have obtained through experimental evaluation, and then we see the major takeaways. So the first thing is that what is MCDC? Modified condition region coverage. So MCDC is the second strongest coverage criterion in unit testing after NCC, that is multiple condition coverage. Actually, MCDC requires linear number of test cases with respect to the number of conditions present in a program, in contrast to the MCC, which is combinatorially explosive because it requires 2 to the power n number of test cases. So, and MCDC requires the following requirements. It requires each entry and exit point should get invoked at least once. Each predicate in the program must take both the truth values, and each atomic condition in a predicate take both the truth values at least once. And all these three requirements seems like are actually statement coverage, decision coverage, and condition coverage. But the fourth one, that is like mainly for MCDC, is each atomic condition in a predicate shown as independent. Here, the independent means to show a condition as independent, we have to flip the values of that particular condition by keeping the all other values as it is, and if by flipping that value, if the result of predicate changes, then we can say that the condition is independently affecting the predicate. Now, why MCDC? According to RTC DO 178B and C, it is mandatory to achieve level A certificate. It is mandatory to achieve MCDC to obtain level A certificate for safety critical systems. Now we will see a survey. In our survey, we have participants from different industries like avionics, automotive, medical devices, railways, but we can see like majority of our practitioners are from avionics domain, and then we have listed several MCDC tools, and among those tools we can see that LDRA and VectorCast are the two most popular ones. We have asked our practitioners, participants, that whether their approach is automated or like partially automated or manual. So from this pie chart we can see like only 20% of the participants are using fully automated techniques. Then after that we ask them if their MCDC score is low, so what they do, means what approach they follow when they obtain low MCDC score for a program. So most of them said they use manual techniques to generate the missing MCDC test cases, or sometimes they fix issues in the code or use some other MCDC tool. So by this survey, we can say that there is a huge requirement of automation in MCDC for MCDC testing. That's why we have proposed our idea, and this is the overall architecture of our framework, where we have used dynamic symbolic execution with cluster interpolation to generate the required MCDC test cases by using annotated LLVM IR. So first we extract the predicates present in the program, and we supply those predicates to the sequence generator to generate the sequences, and Along with the sequences, we supply the LLVM IR to the resource annotator, which annotates the LLVM IR based upon the required sequences, and then we supply the IR, updated IR to the dynamic symbolic executor. So, for example, in this example predicate, where B is less than 0 or C is less than 0 and D is less than 0, for this, our sequence generator has generated 5 short-circuited sequences, since we are using the short-circuited MCDC, and S1 to S5. So in the first sequence, the values are like true, don't care, and true. These are the sequences, and we represent the true value with 1, false with 2, and don't care as 0. We are using these integer values because during the annotation, we have added the arithmetic formulas in the basic blocks to encode these values or to generate those sequences using the ghost variable, that is kappa. So for true, we are just incrementing the kappa value. We are multiplying the kappa value with 10 plus we are adding 1 for true value, and for the false, we are incrementing with 10 and multiplying 10 with 10, and then we are incrementing with 2. Every time we are incrementing, multiplying the kappa with 10 to encode that particular, to maintain the encoding. So these are the 5 short-circuited sequences and their corresponding part in the CFG. Now, after that, we use the dynamic symbolic execution. So, and one more thing, that we insert all the sequences, like after all the sequences, we insert the assert function in the last, after the predicate with all those sequences, and we believe that if we get any assertion violation, that means that path is feasible, and our executor will generate test case corresponding to that particular path. Now we see the taming of path explosion. As we all know that the path explosion is the major problem of symbolic execution. So for this, we have used abstract learning. In the abstract learning, we have used for this, we just prune the already traversed trees based upon, so in this, for each of the path, already visited path, we generate interpolants, and we combine path interpolants to generate a tree interpolant, and whenever we revisit the particular program point, we see if the context of that revisit point implying the generated interpolant. So if it implies, then we prune that particular program, particular subtree. So we can understand this with an example. So in this example, we can see that we are trying to prove that x is not equal to 28. So this is the corresponding symbolic execution tree where the program point 4a and 4b are same. And when we are traversing 4a, when we reach 4a and we traverse these two subtrees, and we have obtained this particular interpolant for program point 4a, and later on when we came to 4b and we found that our context is implying the interpolant already at 4a, so we have not explored the subtree below 4a, and that's how we are doing the subsumptions, and we are pruning the execution tree. Now this is our custom interpolation that we have built upon the standard interpolation, that is TracerX system that I have already discussed in standard interpolation. So in this, along with the already generated interpolants, we are also maintaining the kappa value generated interpolants, so that we should not revisit the sequences, that if we have discovered the MCDC sequence, then we have just removed those sequences. So this is the add-on on the standard interpolation. For example, in this, like this is the old predicate that we have seen, and with this we have added one more condition, And then this is the execution tree for that example program. And in that example, we can see that when we are coming from node 1, 2 and node 4a, we have a infeasible path, because here the condition b is equal to 3 and we require b is less than 0. So to maintain this infeasibility, we are generating an interpolate b equal to 3. And then when we traverse back to the right path, we have explored these sequences like 211 and 212 from 6a node. And this for 6a node, we have the interpolant kappa should not belong, that kappa have a set of 10. And then for this 5a, we have explored this sequence 220, and we have this interpolant for 5a node. And when we are revisiting the 5b, we saw that our context here implying this interpolant, so we are not exploring this part. This is how we are using the pruning as well as we are finding the sequences. Now we see the experimental evaluation. We have used this setup and we have kept the timeout of 1 hour, and our results can be accessed from here. So in our main experiment, we have compared our proposed custom technique with CBMC, because CBMC is only known tool available which supports the MCDC and which has the MCDC option, and it gives the feasible and infeasible sequences. And in our supplementary experiment, we have compared with no interpolation, that is KLEE, standard interpolation, and our with custom. And in our experiment, we have included 210 programs. Basically, we have taken programs from Psycho series like SECOM and from RDL's challenge from year 2012 to 2020, and we have total of 210 programs. So mainly I would like to highlight the difference between KLEE and the standard interpolation and custom interpolation. Similar to KLEE, we use forward symbolic execution to find the feasible paths. However, we are maintaining the intermediate execution states in order to generate the path interpolants, and then we are combining the path interpolants to generate the tree interpolants, and then we are using those full interpolants. Those are, I'm saying, tree interpolants to make the subfunctions as similar program points. And the difference between the standard interpolation, that is TracerX, and the custom interpolation is that custom is designed to discover MCDC sequences and it generates test cases for those sequences, unlike TracerX, which is used only in case of safety. And symbolic execution typically stops the path on witnessing a bug. In contrast, custom modifies that particular interpolant and continue the path. And also in custom, we generate weakest interpolant on the ghost variable alongside the standard interpolant on rest of the variables. So,
is that lost focus? Or? Okay.
Yeah. Sorry. So mainly we have divided our experimental results into 4 groups. In the first group, we can see that both the custom and CBMC terminate. In the second group, custom terminates but CBMC doesn't. In third group, CBMC terminates but custom doesn't. And in the fourth, neither of the tools terminate. So from this first table, we can see that our TracerX is able to terminate in, our custom is able to terminate in 162 programs, whereas CBMC terminates in only 96 programs. And also, if we check the number of sequences that are proven, so our tool custom is able to prove 531.2K sequences, whereas CBMC is able to prove only 104.7K sequences. So there is a huge win. And then this is the scattered chart for the proved and unproved sequences between CBMC and custom. So from this chart, we can see that the number of red dots are really high, which shows that custom is able to prove so many sequences, whereas in this, the green dots are really visible because it is showing the number of unproven sequences, that is by CBMC. Now there is a comparison of time between KLEE, standard interpolation, custom interpolation. So we can see that in this print eclipse over, so that the timeout happened for so many programs for KLEE, and there are some programs on which timeout happened for standard interpolation, but we can see that custom is able to finish in all the programs. Okay, and these are the subset of programs from those 210 programs. These are only 6 programs, and then major takeaways are like symbolic execution is especially designed for these 2 things: bug finding and program verification, whereas we have used symbolic execution to discover MCDC test cases based upon the sequences, and our custom interpolation is clever enough to prune the subtrees which contains already discovered MCDC sequences. And as if our algorithm terminates, then it generates optimal set of MCDC test cases. Also, like I will conclude with highlighting that our survey says that MCDC generation is really inadequate in the practice, and most of the practitioners are relying on manual effort. However, if you see our method, that it gives optimal set of MCDC test cases if the program terminates, and our custom is far better than CBMC, and our experimental result proves that. And these are some of the references. Thank you.